Okay, good morning Year 6 and welcome to Monday's maths lesson. This is the third lesson in our algebra sequence, and today we're going to look at how we can use simple algebraic inputs. Okay, moving on to the warm-up. So if you'd like to have a look at these questions, pause the video and then I'll go through the answers in a moment. Okay, question 1. What is the output if the input is 12? Okay, so we input 12 into the function machine, we multiply it by 3 and we get an answer of 36. We then add 7 to the 36 to get an output of 43. Question 2. Work out 40% of 60. Okay, so a good idea to work this one out is actually to find 10% first. It's always a really good idea to find 10% because that's really easy to find. How do we find 10% of something? Well, we divide it by 10. So 60 divided by 10 is 6, or 10% of 60 is 6. So once we found our 10%, we then need to just multiply the answer by 4. And 6 times 4 is 24. So 24 is 40% of 60. Okay, number 3. What is the 4 worth in 6.145? Well, we can see that the number 4, or sorry, the digit 4, is in the second decimal place. That represents the hundredth, so it's worth 4 hundredths. Number 4. Write down 2 factors of 20. Okay, so when we find out factors of a number, we always work systematically. Okay, so we know that 1 times 20, or 1 and 20 are factors of 20. We know that 2 and 10 are factors of 20. We also know that 4 and 5 are factors of 20. So any of those 2 would have been the right answer. Okay, so here's a little picture of Snoopy for you. So our learning focus today, I can use simple algebraic inputs. So last week we met 1-step and 2-step function machines with numerical inputs. Well, today we're just going to change the way that the inputs are symbolised. So in this step you will use simple algebraic inputs instead. So e.g. y or x or a. They're called algebraic symbols and they represent different numerical inputs. So they could stand for any different numerical input. So using these inputs in a function machine will lead you to form expressions. So for example, y plus 4. That's where we've got the algebraic symbol alongside a mathematical procedure or calculation. We will use cubes to represent a variable to aid your understanding in the slides that I show you and in the questions. And today you will be introduced to conventions that we will use when writing algebraic expressions. And this is something you need to remember, okay, because not only does it come up in Year 6, but when you go to secondary school and you work on this in Year 7, Year 8, etc., you're going to need to know this. So this example here, when we have y times 4, or x times 4, or a times 4, or any algebraic symbol times 4, we actually write that as 4y. So the number you're multiplying by goes in front of the algebraic symbol, and the multiplication sign isn't included at all. Okay, so with addition and subtraction in algebraic expressions, you will see the addition sign and you will see the subtraction sign. In multiplication, you won't see it at all. The number will just go in front of the algebraic symbol, and with division it will just be a line written underneath the number or algebraic symbol, just like you would see it in fraction. The line in the middle of the fraction means divide, doesn't it? So that's what you'll see how it's written in those algebraic expressions. Okay, so let's move on to the first question. Have a little read of this to yourself and pause the video, and then I'll go through the answers with you in a moment. Okay, so Mo uses cubes to write expressions for function machines. In the first example, we've got the input number, we add 4, and then we've got an output number. So here the input is represented by a cube. Then we do the function that's on the function machine, and then the output will be the input plus 4. We can see 4 here. Now how we write that as an algebraic expression is we start with our input representing it as an algebraic symbol. So in this case we've used y. it goes through the function machine, and the output is y plus 4. That's how we would write it. Okay, in the second example, here we have the input again, which is represented by a cube, or on the bottom line by the algebraic symbol y. The function of this machine is multiplied by 4. So here we can say here we can see our cube input has been multiplied by 4. Okay, then we've got 4 of the original. Okay, you might want to put there, you might want to think to yourself to write 4 times y. But remember, in the bottom, what we do with algebra, how we express it, is that we actually, instead of saying 4 times y, we say 4y. Okay, 4y. So that means y times 4. But that's how we write it, with the number first. With the number it's multiplied by 4 first. Okay, so use Mo's method to represent the function machines. What is the output for each machine when the input is A? Okay, and in my examples, I haven't used cubes, but you might have wanted to do that at home. So in the first one, the input. Okay, I'm going to represent the input this time as the letter A. It can be any letter, it doesn't matter. Okay, and in questions we look at today, that letter might mean something. So it might be, for example, T might equal time, or it might just be X or A, and it might represent any number. Okay, so I have A. I'm going to put it into the function machine. I'm going to add 2, so my output will be A plus 2. In the second function machine, my input number this time is also going to be A. This time I'm multiplying it by 3, but I'm going to remember to myself, well, what's the convention when we write that as an algebraic expression? Well, my A is going to go to 3A. Well done if you got that right. Okay, next question. This time we've got a 2-step function machine. So Eva is writing expressions for a 2-step function machine. Okay, have a little look at this question on your own. Read it more than once if you need to. Think about the answer, have a go. Pause the video, and then I will come back and go through it with you in a moment. Okay, so here we can see that the input number is represented again by a cube. The first function is multiplied by 2, so then in my mid-step of my function, I'm going to represent that as 2 cubes here, or in the bottom line, I have input of x, and then when it's multiplied by 2, I'm going to correctly write that as 2x. Okay, the second point of my function is add 3. So here we can see we're just adding 3 to the two cubes, and down the bottom, the 2x then goes through the remainder of the function machine and comes out as 2x plus 3. Okay, so use Eva's method to write expressions for these function machines. So the first one, I've got my input number. I'm going to call it x. You could have called it anything you like. Okay, so the first is going through the first function times 3. So I can remember that's going to be 3x. That's my midpoint of my function machine. Then I'm going to put it through the second step of the function, which was plus 2. So it's going to become 3x plus 2. In the second function machine, again, I'm going to represent the input as x. I'm going to multiply it by 5, which I know I write as 5x. That's my midpoint. I'm now going to put it through the remainder of the function machine, which comes out the other end. The output expression is 5x plus 2. Well done if you got all those right. Okay, moving on to the next question. Okay, this time we've got Amir. And Amir puts m into these function machines. Okay, the first one, input, multiplied by 2, plus 1, gives you the output. The second one, the functions acting on this are plus 1 and then multiplied by 2. Now, Amir says the outputs of the machines will be the same. Okay, now, do you agree? Explain your answer. So before you pause the video and attempt to do this, think to yourself, well, how am I going to find this out? Is there more than one way that I can find this out? Okay, pause the video and I'll go through it with you in a moment. Okay, so I'm thinking about this. Well, he's written it and he says they will be the same. Well, how are we going to find out if they're the same or not? Okay, well, I actually thought about it. I didn't just do it one way, I did it more than one way. And I'm thinking, well, no, I don't agree that he's right. And this is my thinking behind it. So, first of all, I've done it algebraically. So I've looked at his function machine, I've written it as an algebraic expression, the output. So I thought to myself, he's got m, he's putting m in there. He's then timesing it by 2, so that makes 2m. And then he's adding 1, so that would give me the expression 2m plus 1. So that's the first output. The second function machine, again, I'm going to input m. But this time I'm going to add the 1 first. So at my mid-term point of the second function machine, I've actually got n plus 1. And it's then that n plus 1 that I'm going to multiply by 2. So you know from using BODMAS, how you would write that correctly would actually be, you'd have to put brackets around the n plus 1 and you times that by 2. And then if we write that using algebraic conventions, we'd write the 2 before the bracket. So that would be 2 brackets n plus 1, or we could expand that out, how they do it in algebra. We would expand that out and that would be the same as 2n plus 2. But even if you didn't understand that little bit there, you can actually see that the outputs are going to be different in those function machines. Right, well, how about if you didn't work it out like that? Okay, well, what could be another way you could work this out? Well, you could input a number. You could try it out, couldn't you? You could try out the function machine. You could put a 2 into both of them and see what happens. So I put a 2 into the first one, and I had 2 times 2, which gave me a midpoint of 4. I then added 1, which gave me an output of 5. In the second one, I had an input of 2. I added 1, which was 3. I multiplied it by 2, and that gave me an output of 6. So I can there see that I've got different outputs. So I don't agree with Amir. Okay, that was 2 different ways of working it out. The first way was a real algebraic way of working it out, but we still got to the same conclusion, didn't we, working out the other way. So as long as you can explain your thinking in mathematics and that, then you're doing really well. Okay, next question. So this function machine gives the same output for every input. So for example, if the input is 5, then the output is 5, and so on. What do you think is the missing part of the function? And what other pairs of functions do you think will do the same? Okay, have a little think about it. Pause the video and I'll come back to you in a moment. Okay, so when I was thinking about this question, I actually used the example that they gave me. So I thought to myself, well, if I'm going to input 5 into this function machine, I'm going to then do what it says there. So if I input 5, the first thing that acts on it will be times 2. So then my midpoint of my function is going to be 10. Now I know from the question that I need to get back to the output of 5. So I could do subtract 5. That will get me back to 5, wouldn't it? Let's try that out with another number. So I could input 3. 3 times 2 is 6. 6 take 5 is 1. Oh, no, that doesn't work. So it must not be minus 5. It must be something else. Okay, so if I put the input of 5, I've times it by 2, I've got a midpoint of 10. How else could I get back to 5? Oh, I know. I could do divided by. I could do divided by 2. Right, does that work with anything else? Let's try it. If I inputted 3, 3 times 2 is 6. 6 divided by 2 is 3. I'm back to 3 again. Right, I think I've got it. I might even want to try it out one more time with another number just to make absolutely sure I've got the right thing. Let's try it. Input 2. 2 times 2 is 4. 4 divided by 2 is 4. Sorry, is 2. So, but actually, I probably don't need to do that because what do we know about timesing by 2 and dividing by 2? That's right, they are the inverse of each other. Okay, so that leads us on to answer the last question there. What other pairs of functions can you think that would do the same? Well, if you added 3 and subtracted 3, that would do the same. If you added 4 and subtracted 4, that would do the same. If you subtracted 4 and then added 4, that would do the same. So it's using those inverse functions that would get you back to the start point. Okay, well done. Right, moving on now. I think you can have a go at the White Rose questions, and I'll speak to you again tomorrow. Thanks, Year 6.